Good morning, students. Today we are going to see about the actinides. So far yesterday we have discussed the lanthanides. In F-block element we have discussed about the lanthanides yesterday. Today we are going to see about the actinides. This F-block element, since it's F-block elements, the differentiating electron enters into the 5F orbital. So it may be called as a 5F series. Lanthanides are called as a 4F series. This is a 5F series. Lanthanides all are radioactive elements. They are very low percentage in the earth crust. You may find thorium and uranium in the monocyte sand. A little bit of neptunium also there in the monocyte sand. All of them are man-made, artificial radioactive elements. Okay. Then let us move on to the electronic configuration. If you see the electronic configuration, the general electronic configuration may be written like this: N-2F, N-1D, and Ns. Okay. How they are filling here? 2 to 14, F2 to 14. Here 0 to 2. Okay. This is the general electronic configuration of actinides. So let us see the tabulation clearly, then you will come to know how the electrons are filling in the actinides. Okay, we take here this is for name, this is for symbol, atomic number, and then electronic configuration. Name, atomic number, symbol is electronic configuration. You need to write 15, so you know. Okay, first one, actinium. Thorium. Then protactinium. Uranium. And then chromium. Amazing. Curious. Berkelium. California. Einsteinium. Fermium. Mendelevium. Nobelium. Last, you are having the Lawrencium. Then atomic number 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 102, 103. actinium AC, TH thorium, protactinium PE, uranium U, neptunium NP, plutonium PU, americium AM, curium CM, berkelium PK, californium CF, then einsteinium ES, fermium FM, mendelevium MD, nobelium NO, lawrencium LR. Okay, this is very simple. Now, very important thing, how we are going to fill in electronic configuration. You know that radon 86. Okay, radon 86, 5F and 6D7S. This is a booklet. Okay, you need to fill. So for 86 we are putting a radon. Writing radon. How many 89 is there? 5F. In actinium is a D-block element, so there is no electrons. 6D1, 7S. So come the number 86, 87, 89. This okay. In thorium. See, before that you should know, in actinide there is no F2, F5, F8. This is another. In actinium. So radon. 0. 16 to 7s. 86, 88, 90. Then protactinium. So 86, 5, 91. Okay. Then radon. 5 3, 61, 7. Okay. Then neptunium, radon, 5 4, 61, 7. Okay. Plutonium, radon, 5 6, no 5, F5 will be there, so 5F6, 6D0, 7S2. Okay, 86. Then americium, radon, 5F7, 6D0, 7S2. In curium, radon, no 8 also, so here also 5, 7, 6D1, 7S2. Then berkelium, radon, 5F9, 6D0, 7S2. Californium, radon, 5F10, 6D0, 7S2. Einsteinium, radon, 5F11, 6D0, 7S2. Fermium, radon, 5F12, 6D0, 7S2. Mendelevium, radon, 5F13, 6D0, 7S2. Then nobelium, radon, 5F14, 6D0, 7S2. Then lawrencium, radon, 5F14, 6D1, 7S2. This is the entire electronic configuration of actinides. See here, how many D1? D1 state. D1 state, see actinium. In actinium, then protactinium, uranium, then for it, neptunium. these are having the D1 and D2 only thorium. You find D2 in only thorium. This is a special case. It is even though it is actinides, it does not have in the. So because the electron configuration is not defined for F, especially for actinides, it is not defined. It means it may be interchanges. Here, 0. Then D1 at last, you will have in a Lawrencian. These are the data you need to have. Then completely filled. F0, you may find in a actinium F0 and thorium F0. Then F7, half-filled electron configuration. Why I am mentioning this is the very most stable. So F7, we will find that F7 in americium and curium. Here, in both, you may find a F7 americium and curium. F7 is half-filled, empty, half-filled. Then completely filled, if you want to go for the completely filled F orbital, F14. F14, you may find here in nobelium and Lawrencium, you are having completely filled F orbital, 14. They are mostly stable. Half-filled and completely filled are most stable. Then a question may be asked, what the F7, where is there? Like this, so many questions may be asked. So for looking, it's too difficult to memorize. Nothing but you must know that elements present in actinide and the atomic number also easy to remember. If you know first, then you can continuously write 89, 90, 91, this number only. If you memorize it, it's very difficult. How to learn this table? It's very simple. Just you study the elements first and their symbol. The atomic number very easy. You starting with 89, 90, 91, 92, like this continuous number. So it is easy to recall and reproduce. Then the electronic configuration, you should know the outline electronic configuration of actinide. Radon 5F67S. Okay. Look here, S can be easily filled in all 15. You may find all SR2222. No changes. Very easy to reproduce. We need not bother about the S. 7S, all of them too. If the problem arises where how the F filled. So before that you should know how many D electrons are filled. In actinium already this D block element, so D1 will be there. In thorium, F0 and D2. And protactinium like F2, D1. And uranium, F3 and D1. Neptunium, F4 and D1. Here you need to look over because F5 is not there in that periodic. F5 special cases, F5 will not be there. F1, F5, F8 will not be available there. F1, F5 and F8 will not be there. So F5 will not be here. So here you should jump out to 6. In plutonium, no F5. F6, D0, 7S2. Then automatically F7. Here also helium F8 is not also available. Not known. F8 is not known. So F8 you are putting that F7 D1. Again here D1 also available. So curium. Again, then if you go 8 is not there. So 9, 10, 11, 12, 13, 14. Again you need to put a 14 under D1. So I am clearly pick out in a D1. What are the elements having D1? What are the elements having D2? What are the elements having F0, F7, F14? These are very, very important. That's all about the electronic configuration of actinides. If you go on write once, it will be very clear. The question may be asked, write the electronic configuration of plutonium. If you start with this, you recall what is the atomic number, and you fill the general electronic configuration, what is there, easily. Okay. Then let us move on to the oxidation state of actinides. Oxidation state of actinides. So oxidation state. So variable oxidation state shown by that. Especially +3 is most common. Then variable oxidation state are shown by the actinides. Let us see how they are. Uranium, Neptunium, Plutonium, Americium, Berkelium, Californium, and this Einsteinium, Uranium, Mendelium, and the Nobelium, and Lawrencium. Okay. So thorium and the americium will have +2. +2 only shown by thorium and the americium. +3 all ditto, or 14 also you get +3, +3, +3, +3, +3, +3, +3, +3, +3, +3, +3, +3, +3, +3. So this is why it is a common oxidation state of actinides. For both lanthanide and actinide, +3 is a common oxidation. Then +4 is shown till still berkelium. +4. +5 shown till +6. +7. So all the oxidation state of the F-block elements shown by this americium, +2 to +7. Okay. Then if you can easily recall, +2 and +2 only by thorium and americium. Likewise, you can have the electronic oxidation state of those. All the oxidation +2, +3, +4, +5, +6, +7 shown by americium. So totally oxidation state +2 to +7. Among them, +3 is most common. Americium shows all variety of oxidation state in lanthanides. Okay, so far we have seen the electronic configuration and oxidations of lanthanides. Now let us discuss the difference between the lanthanides and actinides. Lanthanides. Okay. Here the differentiating electron enters into the 4f orbital. Differentiating electrons enters into the 4f orbital. Here differentiating electron enters into the 5f. So first difference. So that's only this is called a 4f series, this is called a 5f series. The differentiating electron enters into the 4f orbital, the differentiating electron enters into the 5f orbital. Then regarding binding energy, binding energy comparatively greater than that of the binding energy is less. Okay, so more and very less compared to these two. Then shielding more shielded than that of the actinides. Shielding only less. So both of them are poorly shielding. That's no worry. Among these two, it is highly shielded comparatively actinides. Okay. Less basic. These compounds are less basic. Here it is a more basic. The compounds are more basic. Then the ions are colorless. the ions are colored. For example, uranium 3 plus red in color, uranium 4 plus green in color, uranium O2 2 plus yellow in color. So this asks me questions. State board and surface meter. What is the color of U4 plus? So you can recall RGY, red, green, yellow. Whereas the ions of lanthanide compounds are colorless. They are colored. Except promethium. Promethium, all are non-radioactive. All of them are radioactive. See, the non-radioactive, this is radioactive. Okay. So only lanthanide, the promethium is man-made, artificial, that is radioactive element. Whereas other than non-radioactive, in actinide, all of them are radioactive elements. Less tendency to form a complex. Less tendency to form a complex. More tendency to form a complex. More tendency to form a complex. Then they do not form oxocation. They form oxocation. For example, PO2 plus, PO2 plus, okay. So these are the main difference between the lanthanides and actinides. Electrons are entering into the 4f electron, electrons are entering into the 5f orbital. Binding energy is higher, whereas the binding energy is less. Shielding effect is more, shielding effect is less. Comparatively, F totally poor shielded. On these two, if you compare, it will be more shielding. Basic character. The compounds are very less basic, whereas they are more basic. The ions are colorless. Lanthanide ions are colorless, whereas actinide ions are colored. For example, uranium 3 plus, U3 plus red, U4 plus green. Uranium oxocation will be yellow in color. Then, except promethium, all are non-radioactive. Promethium is a radioactive substance. Except promethium, all are a radioactive, non-radioactive substance. Whereas all actinides are radioactive, highly radioactive substance. They are non-radioactive, they are radioactive. Then, complex formation, less tendency to form a complexes. They have actinides have a more tendency to form a complex. Then formation of oxocation, they do not form a oxocation. They form a oxocation. For example, you have like this. It will have as any other difference we can have oxidation state we can say. For both of them, plus 3 is most common. Okay, plus 3. Other than plus 3, lanthanides are exhibiting plus 2 and plus 4 oxidation state. Okay, plus 3 for both of them same, common oxidation state. Other than plus 3, minimum plus 2, maximum plus 4 oxidation state exhibited by this one. Whereas here, plus 2, plus 4, plus 5, plus 6, plus 7. So these many oxidation states found by, variable oxidation states found by actinides. These are the main differences between the lanthanides and actinides. Both are them paramagnetic, but it is separation is difficult. That is separation is easy. Okay, that's all about this comparison or difference between the lanthanides and actinides. Then let us see the uses of lanthanides and actinides. uses of actinides only today we are going to see. So uranium-235. Uranium uses uranium-235. Uranium-235, it is used in the nuclear power plant. And nuclear weapon. So uranium-235, it is used in a nuclear reactor. There is a nuclear power plant and nuclear weapons. This is fine used. Plutonium-238 isotopes of actinides. It is used as a power source. Power source in a long mission spacecrafts. So long mission spacecraft, you are finding use of plutonium-238. These are the uses. It is not given in a book. Uranium-235 and plutonium-238. They are found some of the uses of actinides. That's all about the actinides. So dear students, now we are going to recall the whatever we have seen today. Today our topic is to discuss is actinides. Actinides, what are the actinides? Actinides are the differentiating electron enters into the 5f orbital. They are called as the actinide. The position and everything we have seen already in yesterday itself. Then electronic configuration. Electronic configuration, we have listed the from thorium to actinium to thorium. Actinium to thorium. Actinium is a D-block element. Then thorium to lawrencium. We have listed the tabulation and how the electronic configurations are formed. Or electrons are filling into that orbitals. Then we have seen the oxidation state exhibited by actinides. Most common oxidation state +3, least +2, maximum +7. That we have seen already. Then comparison between the lanthanide and actinide. There are some similarity like a lanthanide contraction. Here actinide contraction also available. Actinide contraction is nothing but that's also not given in a book. Just it is a similarity to the lanthanide contraction. What happened to lanthanide contraction? Steady decreases in the lanthanide ions when atomic number increases. Likewise, actinide also there will be a steady decreases of the ions when atomic number increases. Lanthanide contraction is due to the poor shielding of 4f electron, whereas actinide contraction is due to the poor shielding of 5f electron. Then we have see the comparison and the uses of the actinides. That's all about the F block element. Tomorrow we will see the next lesson with a new topic. Thank you.